My name is Dave Whiteley from Envisage, and this is another of our Friday morning webcasts entitled CFDesign, Fluid and Thermal Analysis, and this will last for about 30 minutes. Okay, what is CFD? Well, it stands for Computational Fluid Dynamics. It enables you to analyze both fluid flow and heat transfer. Fluid flow, both internal and external flow to the model that you're analyzing. Laminar and turbulent flow, and you can read the rest, but some important ones are the fact that we can mix, but only between similar fluids, similar states of fluids. Transient means that we can actually analyze a flow through time. Steady state is a single point in time. Heat transfer, conduction, and then both forced and natural convection, radiation and solar, which is a useful one for architects. In the software I'm about to show you, you can also analyze motion. So if you've got any rotating flow or flow of any motion, I beg your pardon, or rotating motion of any sort, that can be analyzed in the software as well. Now, what is CFDesign?
Now joining Trevor Thomas.
Now, CFDesign is an electronic digital flow bench. It is a digital wind tunnel, and it is a digital thermal test rig, all three in the software. The software itself will work associatively with the following CAD products. So a lot of work has been put into the writers of CFDesign so that you've got associativity between the products that you can see on the screen. I'm going to go through four different types of analysis on the PowerPoint, and then I'll be showing you a mechanical analysis of fluid flow as an example in the CFDesign software. So we're looking at mechanical, electronic design, analysis of LED lighting, which is an important analysis required at the moment, and architectural analysis as well. So for mechanical, we're looking at things like pumps, valves, and the typical problems that we see with these is that we want to analyze pressure drop. Anybody who's designing valves will know about cavitation. We want to know about recirculation regions and so on, and fluid flow characteristics throughout the mechanical design. So for instance, in this example, we've got a valve here with different apertures in the valve, as you can see, and we would want to analyze the fluid flow through this valve with these different models, and produce an analysis where we can contrast and compare between the results on the software. Problems that we have with electronics are temperature gradients, very large temperatures that we want to avoid, fan sizing and placement, slots or aperture sizing and placement, flow patterns, a very important heat sink performance. Anybody who's had a Microsoft Xbox, I think it was, had a problem with a heat sink, and you can redesign your electronic equipment and analyze for heat sink performance. And we're looking at component level, PCB board level, and a complete system level should we wish. These days, a lot of companies are retrofitting LEDs to their lighting to reduce power costs and so on and so forth. And a big problem with LEDs are temperature gradients. Junction temperature at the LED is vitally important. And because they're retrofitting, then they have to redesign a certain amount of the light system to allow for the temperatures, or to reduce the temperatures within the LED light. So these are the sort of challenges that they're faced with lighting. Big requirement at the moment, where you want to analyze fluid flow through office buildings, cool rooms and so on, from air conditioning units, reduce or increase the efficiency of air conditioning units and so on, and also wind loading or wind loading on buildings, and also solar loading on buildings as well. So all this can be done in the CFDesign software. Don't be put off by the fact that this is a water fluid flow analysis. Same sort of principles apply to electronic analysis. So what I'm about to show you, if you're into electronics, watch it. You will understand, hopefully, how it will work in electronics assemblies as well. So what I'm going to do here is we'll have a look at this design. It's just consists of a divider internally and a pipe body. It is important when you're running analyses to simplify your design as much as possible. You don't really want to be having a 2,000 part assembly and then trying to analyze that in your analysis software. So you simplify as much as possible. As an engineer, you would know what to do. So the objectives here are that we want to assess the fluid distribution through this tap. We also want to assess the temperature uniformity of the water on exit of this tap. We want to measure the pressure drop from the inlet to the outlet. And we want to compare the pressure drop after alteration to the system. So if we alter this design in some way, we want to compare the values that we're trying to assess from this between the different scenarios. Okay, so what we're going to do is run this through the CAD plugin for the software. You will have a plugin for your CAD system that will enable you to push this through to the CFDesign software. This will read the model into the CFDesign software. Okay, so what we've got here is because the interior, the water inside, or the water volume inside this model hasn't been modeled in the CAD system, if these inlets and outlets are closed off, the CFDesign software will automatically create the volume for you. But you do have tools available to you in the CFDesign software to enable you to either add an external volume or an internal volume to the model. So what we're going to do here is add surfaces to the inlets and the outlets. And then we'll fill that void with a solid. So now what we've got in the CFDesign software, I'll just rotate this around, is that we've got the external body. We have the, in this case, the water volume inside the mixer tap, and we have the internal components as well. Now we need to add some materials to these. If we're concerned about fluid flow, we only really need to worry about the water volume. If we're worried about temperature as well, we also need to be concerned about the external and internal components and their materials. So in this case, I'm going to add materials to these. So the external component we'll make from. And we have a list of types of materials we can add to our models. Those of you in electronics will notice that we can add thermoelectric components, we can add PCBs, and we can edit the PCB for multi-layers, how much copper, what material the PCB is made from, and so on. LED devices, compact thermal models. Anybody in valves and so on, we've got check valves, rotating regions. In electronics, we've got fans. We've also got pumps and blowers and resistance and so on. So we can add various types of material to the models. In this case, we've got a solid model, and we want to make this copper. Okay, we'll just turn that one off and get to the water. And we'll edit that one, that's a fluid, and from a list of fluids, we're going to choose water. Turn that one off. And last but not least, the final one is solid, and that'll be copper as well. Okay, so now we've added the materials to these. Now we need to add some boundary conditions. So we just go to boundary conditions, and we've got a velocity on the inlets that we want to add to the inlets, the cold and the hot inlets. And we'll add a velocity here of 7,500 millimeters per second. We want an inlet temperature of 50 degrees C on the hot inlet, and on the cold inlet, temperature of 7 degrees C. And then on the outlet, we need to tell it that this face here is an outlet. So we're going to add a pressure here of 0 to make this an outlet. Okay, there's our boundary conditions set. Now we're going to mesh it. So I'm going to mesh this automatically. Let's go ahead and mesh this and then we can talk about this. I'm going to mesh this automatically, but you can, as per most systems, change the meshing to, of any of the parts should you wish. This will actually auto-mesh. You are able to edit the mesh with purely a slider. There's lots of uses of sliders in CFDesign, which makes life as an engineer much more easier. But you have full control over the mesh of the parts in this assembly. I'm just using an automatic mesh at the moment, and we'll just have a look and see what results we get. There's the mesh. We've also got our boundary layers created on the liquid, as you can see on the inlets here, these 3 boundary layers. And there's our mesh created on model. Okay. So now we need to solve this. I want to solve it for fluid flow and heat transfer. So I want flow and heat transfer solved on this. And I'm going to run this for 20 iterations. I'll talk about this as we actually run this. Okay, now what it's doing is, you'll see on the screen in a few seconds a convergence plot, where what it does for the first 20 iterations that I specified, it will do the fluid flow analysis and converge hopefully to 20 frames, 20 iterations. You would normally run this for about 100, maybe 300 iterations, because obviously this is a video, or will be a video and a webcast. We want to run this as quick as possible, but I would be concerned about accuracy unless I did increase this. After 20 iterations, it will then run a further 50% again and converge, just analysing the temperature. So you'll notice a red curve appear after 20 iterations once it's done the fluid flow analysis. And then the red curve will kick in, which will then do a convergence of the temperature of this analysis. And eventually this will plateau off. Again, we would really want to have more iterations for this and give us a result. Once this is finished, the next thing we really want to do on these results, as per the beginning when we were looking at the model, is we want to assess the flow distribution through this design. So what I'm going to do is I'm just going to go to my planes and add a plane through the design and perhaps align it with the y-axis and then just drag it up so we can see the velocity gradient through our mixer tap, as you can see there. I'm going to take a snapshot of this for future use. We'll use this later on. The other thing we can do is actually show vectors, which will become more useful. A vector diagram enables you to show things like recirculating eddies and vortices and so on. You'll see some arrows there. I'm just going to edit these so we can see these a little bit easier. So we'll just go to the control of this and just add more vectors to our design. We can also change the size of these. Again, all from sliders, much easier to work with. And you can see we've got recirculating vectors here showing vortices and so on that we could actually design out should we wish. And the other tool we have, if we just turn these off, another tool we have traces, where we can add some points to our plane. It's roughly both on the hot inlet and the cold inlet, and we can add this as a trace set so we can show the velocities of these traces as they run through the design and through the inlet, the internals of the mechanism, and back out to the outlets here. And these are all color-coded against the velocity magnitude or the temperature gradient, whatever you want to watch. And again, we'll take a snapshot of this one for future use. And I'll just turn these off. One I wasn't going to show, but it actually could be quite useful, is to actually show that we can show ISO surfaces. Now, ISO surfaces are useful to show the common, it's like a surface that runs through the design where you can show where common velocities or temperatures are as they enter the design and exit the design. And again, we can use the slider to show these ISO surfaces where we're showing just purely a common value as it runs through the analysis. Extremely useful tool. Okay, what we're going to do now is have a look at the temperature gradient at the outlet. So I'm just going to go back to my planes, and we're going to align our plane with the outlet of the mixer tap, and we're going to change our results to temperature. And here you can see straight away the temperature gradient that runs along across the outlet of this mixer tap. And what we're going to do here is we're going to create an XY plot of the temperature across from one side of the other to the other of this outlet, and plot this as a plot against temperature against the distance across the outlet. And I'll change that, I'll save that for a summary for later on when we're looking at a multiple scenario. Last on this one is to assess the pressure drop. So what we're going to do is we'll change the plane to align with, say, the hot inlet. So we've got a plane there. And we'll go into what they call the design study bar. And we'll update all the values for this. And this plane, if we access this plane, will now show us the area of the plane, the volume flow through this plane, and the pressure at this plane. And because we know the outlet pressure is 0, we can then, from this, establish the pressure drop through the system from the hot inlet to the outlet, as an example. And here we can obviously change the units in which we want to view these. Okay, now what we're going to do now is we'll modify the scenario. So that's our first scenario done with the CFDesign software. What I'm going to do now is just right-click onto the scenario and clone it. So you can clone a scenario like you can with most FEA software and make a new scenario out of this. And I'm going to go to the boundary conditions and change the inlet pressure. So we just go and change the pressure here to 4,000. Sorry, the velocity, I beg your pardon. And on the cold inlet, we'll change the velocity there. We've got a drop of pressure, basically. And then we'll solve this again. The meshing's already done. So all we need to do is solve this again. And this will run the solver for this tool. It's already been, for this design, it's already been meshed, so it'll just run the solver. And this enables you as an engineer to take your design, modify it, change boundary conditions, run the analysis. Everything that we chose earlier, for instance, images of results, planes where we wanted to know the velocity or the pressure at that plane, XY plot data of temperatures across an outlet, for instance, will all be created for this second scenario automatically. Another thing you can do is, if you're doing the same sort of analysis all the time, you can set up templates. So instead of me having to choose boundary conditions and add materials to this model, if you set templates up, then the template enables you to very quickly just drag and drop onto predefined boundary conditions in this tree here to enable you to actually do lots of analyses very, very quickly on different models. So we're just finishing the convergence plot for this analysis, and then we'll have a look at the results between the two. So once it gets to iteration number 40, it should finish on this. Okay, we'll now update the values for the results. Okay, now let's have a look at the summary plane. In this instance, I want to look at the pressure drops between the two scenarios. So I'll just say that I want the pressure drop shown. I want to plot the pressure drop itself. If I now click on plot, what it will do is it will show me the two scenarios that I've got in my design and my analysis here. And in this instance, it's actually showing the pressure or the pressure drop because the outlet is 0 of the two systems. So as I decrease the velocity, then I get a different pressure drop across the system. Let's also have a look at the XY plot that we showed earlier. This is the temperature distribution across the outlet. And as you can see on the first scenario where the pressure is higher on the inlet, we've got a larger temperature distribution across the outlet. And as we reduce the pressure on the brown second scenario, it's showing the temperature gradient across the outlets has reduced somewhat. The other thing we can do is take our images and show these. If I just drag the second one into the screen, the great thing here is we're able to automatically flick between the results of many scenarios on the screen and visually see the differences. In this case, we've got the velocity through the system. The great thing here is it doesn't actually change the bar, the results bar, which some systems do. And in this case, then we can show the difference in velocities between the two scenarios. And if I go to image number 2 and drag that one across, again we can show the particle paths of the velocity distribution through our design, and again compare between our two different scenarios. So that gives you an overview of a simple example of a fluid analysis within CFDesign. If I go to the PowerPoint here, so the whole idea of CFDesign is to enable engineers and designers to analyze, run analyses, fluid and thermal, on their designs, and most importantly, as we're finding out speaking to customers, reduce costly physical prototypes. Companies are having to reduce the number of physical prototypes they create and the costing of the prototypes. In certain instances, the cost of the software outweighs the cost of the physical prototype, as you probably are aware. For more information, obviously, please contact me if there's any other webcasts you would like to see in the future.